Okay, we're looking at the 1989 M1. So when we look at this problem, this is going to be a conservation of energy. So it's a 0.1 kilogram block is released from rest. So that's over here at point A. Whenever you do conservation of energy, it means no matter what, anywhere, the energy is going to be the same. So the energy at A is going to be the same as the energy at B, which is going to be the same as the energy at C. Okay, so that's what we do for conservation of energy. So there's a lot of information here that give us this vertical distance h above the ground. It slides down the track. It's circular. So here, remember this is going to be uniform circular motion. Here's my radius. It goes up 30 degrees. It's 4 meters per second at point C, which is a height of 0.5. All right, so determine the height A. So to find A, because they gave us the speed here and we know the height, what I'm going to do is I'm going to do conservation of energy between point A and between point C. So to do that, I would say the total energy at A is equal to the total energy at C. So the total energy, I would say, is the potential energy, U naught, gravitational. There's no spring, so we don't have to worry about the potential energy stored in the spring. So U naught plus K naught plus the work done by friction is equal to UF plus KF. Now, what I want to do is I want to say what is zero. So there's no work done by friction because it's frictionless. At the top, when it's at rest, this means the kinetic energy is zero, so it's all gravitational potential energy. So this is also zero, and then this is equal to that. So we have mgHA is equal to mgHC plus 1/2 mvc squared. So they gave us this, and they gave us this, and the only thing we want to find is this. Now it's basically algebra and substituting in values. So I wouldn't start substituting stuff in, and you don't want to make any algebra mistakes. So because I want to solve for this, what I'm going to do is rearrange the equation to solve for the unknown in terms of the known. So I'm just going to move that over, and I'm going to say HA is equal to mgHC plus 1/2 mvc squared over mg. Now I can clearly see I can cancel an m from everything. So I'm going to say GHC plus 1/2 BC squared over G. And then I can see I can factor out a G if I want. Why am I doing this? Because this is how people make mistakes on the algebra, not the physics. So I can divide by that and say HC plus 1/2 BC squared over G. Or sometimes they want it all in terms of variables. So HA is equal to 0.5 plus 1/2 of 4 divided by, we'll just say 10, and 16 times 0.5 divided by 10. So when we do all this, we end up getting 1.3. That's HA. All right, point B, on the figure below, draw and label all the forces. So I forgot to draw it. There's just a dot here. So basically what they want us to do is, at this point B, what does the free body diagram look like? So at point B, you're going to have the weight acting down. So F of G is equal to mg. Now, because this is pushing, remember our contact force is a normal force. So now I have the normal force acting in this direction. So this is my free body diagram. We never, ever, ever, even though it's going around a circle, we never draw centripetal force on a free body diagram. The centripetal force is the net force. Remember, when you're saying F net is equal to MA, and you're looking at it, all right, so now part C says, determine the magnitude of the force exerted by the track on the block. Okay, so So that means that we want to find the normal force. And when we do this, we're going to say, this is part C, F net is equal to MA. And we know that Fn, looking at Earth, is going to be equal to the mass, and the centripetal acceleration, because it's going towards the center, is going to be v squared over r. So now when I solve for the normal force, I'm going to have Fn is equal to 0.1 kilogram times 4 meters per second squared divided by 0.5 meters. And when I do all that, that comes out to be 3.2 newtons. All right. Now, we're going to do part D. It says determine the maximum height above the ground attained by the block after it leaves the track. Okay. So when I look at this picture, this is going to be a projectile. So it's going to go, it's leaving with this velocity, and it's going like this. They already tell me this height. So I want to find this height above the ground. Okay. So for part D, again, when it's leaving the velocity at C, this is my velocity at C. Okay. So because it's a two-dimensional motion, I'm going to have a horizontal and vertical component. So this would be VCX and VCY, and this is 30 degrees. So because we want to find the height, we just need this everything in the y direction. So I know that VCY is going to be VC sine of 30 because it's opposite the given angle. So VCY would be, what was VC? 4 sine of 30. So VCY comes out to be 2. Okay. So how should I do this as a projectile? Well, when I think of all my kinematic equations, I need to think of a kinematic equation that has y in it. So there's more than one way to do it. Like I could find the time, and then I could substitute in for the time, but then I would be doing it in 2 steps. So what we're going to do is we're going to think about a projectile. And again, we're just worrying about that little height that's going to go like this. So when we want to find this height here, if this is my initial velocity, so this would be VCY naught, up at the top, the vector goes like this. So V CFY is 0. Okay, because it's all horizontal and has no vertical component. So if I use my equation VFY squared is equal to V naught y squared plus 2GY, remember, when we're doing projectile motion, everywhere that there's an X, it becomes a Y. Everywhere there's an A, it becomes a G. And then we're going to use a subscript that we're in the vertical direction. So we're going to solve for Y. So VFY squared minus V naught y squared over 2G is equal to Y. Well, this is 0 because it's vertical. So it's going to be negative 2 meters per second squared over 2 times negative 10 and stuff. And the negative in the numerator cancels. So anyway, with the denominator, so 2 squared is 4 divided by 20. So that comes out to be 0.2 meters. But remember, that 0.2 is only from here to here. I have to add the 0.5. So the height is going to be 0.2 plus 0.5, which comes out to be 0.7. All right, that was part D. And then for part E, it says another track has the same configuration but is not frictionless. So now there's work done by friction. And it's still going to have the 4, but it has to be 2 meters to determine the work done by the frictional force. So again, you have your MGH at the top, okay, plus my work done by friction is then going to be equal to that MGH. So I could move it on the other side. So you have your MGH at 2, plus the work done by friction is going to be my MGH at, what was my height? 1.3. Okay. So basically the mg is the same, so it's going to be, whoops, let me move this up. So it's going to be mg, the 2 minus 1.3 is going to be my work done by friction. So the mass is 0.1 times 10 divided by 0.7, and that's going to give me the work done by friction. Which should be 0.7 joules. Oops. The physics on this isn't so bad. You just have to make sure you don't make little mistakes like this one. You have to add the 0.2 to the 0.5, because sometimes I want to say they try and trick you, because if you look carefully at this, it says the maximum height above the ground. Okay, because a lot of times people are used to doing projectiles where this is the ground and you're finding this height. So you have to remember to add those two together. So this is kind of like a roller coaster problem, even though it would be just like a roller coaster, except it's a block sliding, same thing.